All right, well, we're getting rolling here. My name's Will Shewart. I've got the privilege. We good? Mike? I thought I was loud enough. I got two kids. As Nate alluded to, Nate was the actual former program manager of Pathfinder before he became TAK director, and I took over for him. And today I'm here with Melissa Pham and Jimmy Carter, the president. He's back to present Pathfinder 3D. It's a vision-based navigation program providing updates in the absence or degradation of GPS. And so there's our contact information. You'll see this again later on. But what is Pathfinder? Before we get into the TAK components. So in denied or degraded environments, how do you know where you are if you don't have your GPS? And so that's where Pathfinder comes in, using organic to the system, could be dismounted in terms of ATAK or mounted in terms of other camera sources, to derive your position. And so several of the tenets of the Pathfinder program is that we really focus on long standoff, feature-less environments. So been lots of things out there doing, Google Street View and buildings and high-resolution 3D models and in interior cities and things like that. But what do you do when you're not on a road? What do you do when you don't have a ton of features in your field of view? So we focus on long standoff. Sensor agnostic. So yes, we're going to talk about our TAK application here using the Samsung S23 program record phone. But we're also looking at other devices as well, integrating those. So long-wave IR and thermal, you'll see from Jimmy some of that. Other types of passive sensors. So things like integrating other sensors. Yesterday you heard from Open Sensor Hub. Things like wheel encoders and other types of IMUs in conjunction with vision. So integrating all that. Another big thing about Pathfinder is the geospatial data at the edge is very voluminous. How do you get it there? How do you distill it down? And so we've developed a lot of compression techniques and then distilling that information down to the most pertinent information. So my background is GIS remote sensing. Been doing it for a long time. And when web mapping first came out in the early 2000s, it was like if you're a GIS person, you put a map on the web, it was like, I've got 100 layers and you're going to see 101 of them. And so that really can't happen at the edge. And so, how about that geospatial data compression? And really it's one of the biggest things is a GOTS solution. So nothing against industry, but the idea that government can support government and reduce the cost of licenses and things like that. And in terms of the application for Pathfinder, it's not just about whether or not a mounted or dismounted application goes into a degraded environment, but what do you do if you're in a degraded environment and you need to initialize? Where do you get that from? And so that's what Pathfinder can help you with. So, transition. We've got a couple of different transition pathways and partners. But on our dismounted side, I'm working with Soldier Warfare and also ISNA on DAPS2 to help them sort of initialize. And in our mounted, we've got a program that we're tying into with C5ISR and Aperture, and that's a few years out. Work with a ton of different industry partners. TRX, Psionic is a non-imaging LiDAR system out of Hampton. We've done a bunch of work with Leidos down in Huntsville. And then we've got a bunch of academic partners that we're collaborating with on algorithms. So what is Pathfinder? How does it work? Very simple. There's really two parts to it. The first is what happens before an operation happens. So we would go to an area, geographic area, and we'd say, okay, we're going to operate in this 100-kilometer area. We download our geospatial data and we process it. What does that really encompass? Well, we actually take, and currently we're working with synthetic horizons. The idea that we can generate a grid of synthetic horizons that are then saved in a geo package and loaded onto, in this case, the TAK device. The second part is what happens on the device in the field. So as the soldier, whether it's mounted or dismounted, goes out into the field, they would then do the second part of that, and that's what you're here to see from Melissa. And so graphically what that looks like is something like this. We're in the standard shareable geographic data format, SSGF. So we're talking about things you can get from grid potentially, or other types of locally collected data, such as drone-based digital surface models. So we're collecting and harvesting all that data, but that's really big. So what we're generating is those important features of horizons and details that then we can match to once we are on our TAK. That would happen in 2 different locations. If it's talking about the Army, it's the Geospatial Workstation. On the TAK side, it could happen on the TAK mission computer. It's a series of Python scripts and codes that generate that synthetic horizon data set. And I'll get to size and things like that. But what I want to do next is, this is what you're here to see. You're not here to see me. You're actually here to see our plugin that we built to actually do this work. And that's where Melissa Pham comes in, and we're going to kick it over to her. So you want to do your slide next?
Hi, my name is Melissa, as Will said. I will now go over the plugin overview. So I'll go over a more higher level overview of what Pathfinder is in our ATAK plugin, and then I'll go over a more detailed technical overview of what our algorithm looks like, and then I'll go over the demo. So for the higher overview, our plugin uses ATAK-GeoCam. ATAK-GeoCam is a plugin that comes with the TAK install. So when the user installs ATAK, all they need to do is go into the plugin management and install and load ATAK-GeoCam. So we use ATAK-GeoCam because when the user takes an image from their phone, it also includes metadata information such as the roll, the pitch, and the yaw, which we use as part of our algorithm. So our ATAK plugin we call Horizons, which is short for synthetic horizons, because the pre-processing step does generate synthetic horizons that we then match with what we call the true horizon, which is the horizon that we extract from the 2D image that is taken through ATAK-GeoCam. And so then once we're able to find the best match between the horizon extracted from the 2D image with the horizon from the pre-compiled GeoPackage database, each horizon is also associated with a location. So when we find the best matched horizon, we are able to display the location on the ATAK plugin. Our project is originally a desktop application. It is written in Python. So our plugin does take parts of that Python code and integrates it into ATAK. So we ended up using an SDK called CheckWPy. Correct. I might be saying that incorrectly, but CheckWPy basically allows us to use a Python interpreter in Android. Eventually, we do want to convert the Python code into code that can be natively used in Android, such as Java, Kotlin, or C++, because there is a bit of overhead with using a Python interpreter in Android. But in the meantime, our desktop application, we are constantly doing research on optimizing our algorithm, making it more accurate and more efficient. So until the Python code is finalized, we will continue to be using Python in ATAK, and then we'll convert the code after. So now I'll go over the more detailed technical overview of our workflow. As Will mentioned, there is 2 major parts of the workflow. The pre-processing step, which is in step 1, where the GeoPackage database is produced, and then the real-time process, which is in steps 2 to 5, which we use in the ATAK plugin. So for our example that we're going to demonstrate today, it is in White Missile Sands Missile Range, New Mexico, and we are using a DSM and DTM data from Vericon and also TandemX, and essentially we use an area of interest. So for this one, we use a 140 square kilometer area, and this generated a database that's about 2 gigabytes in size, which we then store into the ATAK plugin to use. And essentially, this GeoPackage is generated by finding locations within that area of interest, and from each location we get the 360-degree horizon view from it. And they are essentially just lines stored into NumPy arrays that we then store into the geo package. So moving on to the real-time part of the process for the ATAK plugin, the user will first take a picture through TAK GeoCam, and this stores the metadata information such as a roll, pitch, and yaw. Then in step 3, the plugin will extract the horizon. So we have a couple of algorithms that we do use to supplement one another. The first one is canny edge detection. This algorithm finds all of the edges in an image, and we find the horizon by finding the topmost edge in the image. Sometimes, though, this is not completely accurate, as it might include things like clouds or poles, and so we then also use AI image segmentation. A lot of times, the AI image segmentation is able to accurately find the horizon. However, sometimes it does smooth over the horizon. But what we do want to have is a very accurate pixel by pixel representation of the horizon. So when we combine these two solutions, we're able to find a more accurate horizon. Moving on to step 4, once we are able to get the horizon from the image, we then try to find the best match within the GeoPackage database. And then in step 5, we display the location of that best matched horizon in ATAK. So I will now move on to the live demo portion. So when you load ATAK, this is what it first looks like. And then when we scroll down, we can see Horizons tool. So I'm going to click on that now. There are several configuration settings that we have. The first one is that we allow the user to upload their own geo package. So we allow the user to upload new data or to have different area of interest that we use. The next setting is that we allow the user to choose which segmentation and algorithm, which process they want to use to get the horizon from the 2D image. And so for our scenario, we're going to use TensorFlow Lite for the image segmentation along with canny edge detection, as we have found that that is the most optimal for our use case on Android. And then the next setting is match window. So for this one, we have found that when a user takes images with the camera, sometimes the edges can be distorted, and so the match window will take for this one, the middle part, the 50% middle part of that image to match with. But we do allow the user to override this default value. Next setting is multi-azimuth. So sometimes our solution is more accurate when the user takes multiple images from their location with different orientations. And so the user can check this box if they have more than one image that they want to use to find the best location. We also allow the user to indicate whether or not they want to use the top best match or the average of the top 3. Then they can also indicate if they want to use their uploaded geo package or the one that's defaulted that comes with the plugin. They can also save the results to a text file if they want to see the history of what they did earlier. And the setting that is called match using elevation angle, this one was used for when the horizons are doing their matching process. We had a previous version of this plugin where we had the user indicate the camera parameters for the matching process, but using the elevation angle and the range, it allows us to have this feature be camera agnostic. And so when I click on Take Picture, it will automatically load TAK GeoCam, and we also included a few settings here. One of them is we prevent the user to unallow them to zoom because we do want a fixed focal length. We also show that the camera preview size is exactly what they're taking, and so if we go back, there is black parts that we can see on the sides, and so that just indicates that this is exactly what you're going to see when you take the picture. So I'm going to click back now. For our example, we're going to use these 2 images that are taken from White Sands Missile Range, New Mexico. And now I'm going to go back to the video that we have in our next slide. Did I do? Okay, I'm going to skip over this part since we already went through it. And what I want to show you is what is happening behind the scenes when we click submit. So now this matching process is going on, and the horizon is being extracted from the 2D image. And so this is what the image looks like that we uploaded, or one of the images that we uploaded. And sorry about that. Okay, this next image shows us what the canny edge detection looks like, and so it takes all of the edges within that image, and what we're using is the topmost edge for the horizon. And then this image here shows the combination of our different algorithms for the horizon extraction. And so there are actually 3 lines in this image. They kind of overlap each other, so it might be difficult to see, but there's a red line, a green line, and a black line. The green line represents the canny edge detection that we just saw in the previous image, and the red line that is sitting behind the black line, that one is the AI segmentation one, but the red line, it does smooth over the horizon, and so the combination of these will give us the black line, which we then use as part of our algorithm. Okay, so I'm gonna switch over again to the phone because the process completed. This is what shows up when the process completed, and as we can see, this took about 40 seconds for 2 images. And we did use 2 images. The results of the 2 images are shown on the white dots. You might also see that there is a color map. This represents the geolocation score of the images. And basically the green area shows that which areas match the best, and the red areas show which areas match the worst. Our true location is this yellow pin that says mark 111, and as we can see, the 2 white dots are a bit far away from that true location. But when we combine the results of the 2 white dots, it does give us this yellow clover-like icon. And so if I just show the distance between the 2, this gives us 53 meters, which is what is in our desired distance. So now I'm going to pass this on to my colleague Jimmy, who will now talk about advanced sensor integration with our plugin.
Okay, hello, my name is Jimmy Carter, no relation. I only have 1 slide for you here, and this is more about our mounted solution. So we've been integrating with boson FLIR thermal sensors as well. We've been experimenting with a 95-degree and a 32-degree sensor. And the algorithms that we use to detect the horizons are very similar to the RGB images that we've been using on the ATAK device. But the main thing to go over here is that we can integrate with multiple different sensors on mounted solutions and dismounted solutions. So yeah, that's pretty much it.
Okay, so just a couple of wrap-up things. So we did a soldier touch point last October out at White Sands with CivTAK. They're very familiar with the TAK ecosystem. They use it constantly. And so we got a lot of feedback from them in terms of just the ability to use it and then the desired applications for it, the accuracy they want, and user workflows and things like that. And so here's a couple of examples. So image collected on the left, segmented in the middle, and then the result. These were some really good results. Sometimes we're 8 kilometers away. So we're refining that algorithm. The thing here to take home is that vision solutions are passive. So we're not using LiDAR. One of the questions on day one was, why are you not using LiDAR? It's like, well, because if you're using a 903 nanometer laser, everybody can see you. So it's like broadcasting on a battlefield, here I am, come shoot me. So with passive sensors like this, you can get pretty accurate results. And so I'm not going to go through all these details, but these are the kinds of things we like to crunch is, okay, so what is that? If you just take one image, how accurate are you compared to RTK GPS, real-time kinematic survey grade GPS? And so, you know, in terms of we had, you know, we took, you know, that first one there, 12 images, we took one image and we were within 50 meters. And 50 meters for the dismounted soldier was like their gold standard. They came back to us and said, hey, look, it's all ConOp specific, obviously, but if you can get us within 50 meters of our actual location, then we can go do other things to get better at that, right? You might not want to call for fires or something like that with this, but the idea is, hey, do I know where I am? And so obviously, you know, you get to 5 there, we're pretty accurate, but we probably don't want a soldier taking 5 images and then running the solution on it. And so, you know, that was really telling with the soldiers. And so just to wrap up a couple things there, you know, we've got a lot of work that we're currently doing both the mounted and dismounted side. And the idea with integrating all of those sensors is that it can be sensor agnostic. On the mounted side, everything from the thermal camera, which is very important to mounted missions, to low altitude airborne, to taking instead of generating, you know, a synthetic horizon everywhere that we want to go, just generating the ones that are important. So instead of a 140 kilometer area for a database of 2 gigabytes, maybe we can get 400 kilometers for a 1 gigabyte data set. Integrating land cover and other types of features that are more important. So we're sort of integrating a lot of different things. Obviously, it's a relatively young program, but our transition partners are pretty excited about that. And so I'm just going to wrap up with that. There's our contact information, and I'll field any questions. I don't see any live, but we're opening up for questions. Over.
I actually have one question.
Yes, sir.
You're taking pictures for azimuths, right? Have you done studies on whether it's better to take multiple pictures close versus, you know, disparate?
Yeah. Yeah, so the question was, you know, is it better to take 2 pictures that are right next to each other, like, you know, at 180 degrees and maybe 185, or, you know, 100 and then 250, you know, opposites? And actually the opposites are better because you're incorporating some of those, but it's obviously environment specific as well, right? So when we were doing our testing at White Sands, one of the ideas is that there are some applications out there that do close-in, feature-rich environments, urban, right? We're talking about some of these mountains were 25 kilometers away or more. And so, you know, the multi-horizon component is our next step. So maybe that most important feature is only 1 kilometer away, but it's below the horizon, you can't see it. So we're starting to look at sort of incorporating those features as opposed to maybe 30 kilometers out. Yes, sir.
You use 2 azimuths, big
I'm going to let Melissa answer that one.
I think from our testing, it does vary a little bit, but we have found that it varies between 20 seconds to maybe a minute per image. So if you do have like 4, and the more images that you do have, it does tend to be a little less per image, because I think that there is a little bit of overhead with our algorithm for the first image. So if you have 3 images, then that might take a bit less than 3 minutes. Yeah.
And that is something that we're, as we sort of start to migrate, not just the code base, but some of the AI stuff. I don't know if you guys were here on Monday, you saw a ton of AI at the edge on TAK. And we haven't even scratched the surface at doing some more of that implementation. And so we've all talked that we can get that time down with sort of different libraries and different implementation strategies. We actually had a student, Smart Scholar, last year that was it 40% increase in time, a reduction in time in processing, and we only had them for like 2 months. So, yeah, sir.
Yeah. So have you, in developing your artificial horizons, are you accounting for the seasonal changes, right? So White Sands, not a whole lot of seasonal changes, but up in the Northeast, the way the horizon appears in the winter versus the summer.
Yep.
Are you able to account for these in developing the artificial horizons or on the ATAK plugin?
Yeah, actually, that's a great question. So what do you do about, sort of seasonal changes or, things like Paycom that don't really change a whole lot? That's sort of our next step, but we can do a pretty good job at generating those synthetic horizons with leaf off. Jimmy's got a couple of examples where we can sort of see the tops of the trees, through the sticks. If we're talking about oaks and things like that, they still have that general form. So yeah, we're looking at things like that as well. Ma'am?
Do you see any use like on a vehicle like a Striker or something, like using their external cameras to use that instead of like taking pictures?
1,000%. Yeah, so the idea is that our mounted program would feed a program called Aperture, and it's an alt PNT program through C5ISR, and their whole goal is to integrate all kinds of sensors to aid in that PN strategy. And so one of the biggest challenges with integrating PN strategies on vehicles is not every vehicle needs a certain amount of PNT, right? Some need an AJ antenna and some don't. And that's actually sort of the transition for DAPS2 is DAPS2 wants to, or the idea is that soldiers have it, but as they jump into an MRaiser or something like that, does that MRaiser really need that, a huge PN suite, or can they use DAPS2? And so understanding when you go from mounted to or dismounted to mounted, can you use those technologies? And that's sort of our pathway is, yes, we can sort of integrate into that and be part of that entire sensor suite. Sir?
Yes. Do you guys see this migrating to an aviation type aspect at some point in the future?
Yes. Yeah, we've been in talks with Assured Airspace Access about low altitude aircraft and being able to see and operate below 300 feet, and their current solutions don't allow them to operate below 300 feet because they're using active sensors. And so the idea is, can they use horizons and other types of feature extraction because their camera is looking nadir in most cases, and if you're 100 feet off the ground, you're looking at dust, right, or something else. So the idea is looking forward, 100%.
Okay. Thanks.
Yes, sir.
Have you investigated offloading the computation to other more powerful devices?
Yeah, so on the mounted system in particular, we've looked at the MFOX, we've looked at some other types of things on the mounted system to offload some of that, and that goes back to the previous question about moving vehicles and all kinds of sensors. We would have to have some sort of Docker on that system to feed that. There are lots of PN strategies out there, IMUs, wheel encoders, all those things, and Vision can help reset some of those things and do sanity checks on it. So I do think that's a valid application over, yeah, absolutely. Any other questions? Are we close on time? Awesome, 30 minutes exactly. So we're going to hang around a bunch. If anybody wants to sidebar or have conversations, we'd love to chat with you. Thank you very much.